Once upon a time, perhaps around 10 to 20 billion years ago, the universe as we know it today had not yet formed. At that moment, neither space nor time existed in any form we have ever known. This concept is admittedly elusive, yet it lies at the heart of the new way of thinking about the structure, origin, and evolution of the universe. Recent discoveries by cosmologists studying the past and future of the universe have helped answer many long-standing questions. How did the universe form from nothing? Why does it look the way it does? And where will it all end? As physics delves deeper into these questions, it inevitably confronts mysteries that once belonged solely to the domain of religion. The age-old question of whether the universe is the result of chance or intentional design remains a leading research topic in the scientific community. This could foreshadow a remarkable harmony between science and religion, two fields often considered opposites. Most astronomers today believe that the universe was formed from the Big Bang, originating from an extremely dense and intensely hot state. Within this framework, forces such as gravity and electromagnetism are unified into a single force encompassing all phenomena. However, for much of the past century, scientists remained skeptical of this idea. Why does the universe, with its countless galaxies, appear so uniform on a large scale if its initial state was chaotic? Why does the universe exist in a delicate balance between infinite expansion and catastrophic collapse? Between conditions ideal for life on one side and an entirely inhospitable environment on the other? The recent remarkable advances in finding answers to these questions have been achieved through physicists' deepening understanding of the connection between the largest and smallest things in the universe. Thanks to the research of astrophysicists and particle physicists, we can connect the world of stars and galaxies. Similar to the world of subatomic particles and waves, while also proposing theories about their origins. The most remarkable profound insights in recent years have come from Alan Good, a young theoretical physicist working at the Stanford Linear Accelerator Center. He developed the theory of inflation in 1979, explaining the primordial moment of the universe. The formation of matter and many mysterious features of the universe today remain unanswered questions. In reality, the inflation Alan Good predicted triggered the initial Big Bang. Can you explain why matter and energy in the universe formed and even originated from literal nothingness? According to his theory, random factors and chance no longer play a role in the creative process. Perhaps it's not too arrogant to say that God and physics are connected through the concept of cosmic inflation. It wasn't until the 1920s that humans acknowledged the existence of massive galaxies in the universe. William Herschel, a 19th century British astronomer and the discoverer of Uranus, once hypothesized that the faint, hazy clouds of light observed through telescopes were actually island universes similar to the Milky Way. The sun seemed to hang suspended in midair. This was only confirmed when American astronomer Edwin Hubble used the 100-inch Mount Wilson telescope, which resolved individual stars in the Andromeda Nebula. Currently, it is known as the spiral galaxy closest to the Milky Way. The Milky Way, with around 300 billion stars, is just one among hundreds of billions of galaxies in the universe. Perhaps even more astonishing is Hubble's discovery. These galaxies are moving away from us at speeds reaching hundreds, even thousands of kilometers per second. The expansion of the universe brings truly wondrous effects. The expansion means that at some point, all matter could be compressed together at an extremely high density. This implies an easily accepted notion of a stable, eternally unchanging, and perhaps infinitely existing universe. It should be replaced with the concept of an evolving universe with a finite age. From an ordinary person's perspective, this theory makes us question common notions of permanence. At the same time, it opens up the astonishing possibility of a fresh start. Over the years, many scientists have opposed the Big Bang theory. For example, in the late 1940s, Herman Bundy, Thomas Gould, and Fred Hoyer proposed the steady-state cosmology theory. There is no starting point of time there. It suggests that the universe has always existed eternally and will continue expanding endlessly into the future. No matter where you observe from, the universe always appears the same to us. The steady-state model is very elegant and, in a way, deeply theoretical. It avoided the sudden formation of the universe in just a fleeting moment. And life may freely evolve on those planets forever. Our sun may exhaust its fuel in the next few billion years. But there will always be new stars rising to take its place. But in 1965, two scientists at Bell Labs in New Jersey accidentally made a surprising discovery. The paragraph was triggered upon receiving the death signal in the steady-state model. During the restoration of a large horn-shaped microwave antenna, Anno Penrias and Robert Wilson detected a faint but steady radio signal originating from space. No matter what they did, they still turned the antenna in another direction. For a while, they even suspected that the bird-shaped part on the antenna was related to the issue they were facing. But soon after, both they and those around them realized that the sound of slaughter spreading everywhere is the lingering echo of the Great Explosion, resonating across space and time. They detected a uniform microwave radiation, with the current frequency indicating it originated from when the universe was extremely hot. The temperature and uniformity of the radiation perfectly matched the Big Bang model, believed to have occurred approximately 10 to 20 billion years ago. The first 3 minutes. First there was an explosion, but not the familiar kind seen on Earth. Starting from a certain central point and spreading outward, drawing in more and more of the surrounding air with the birdsong. It wasn't a single explosion but a simultaneous eruption everywhere, instantly filling the entire space from the very first moment, as every particle of matter was pushed apart. With our three-dimensional spatial perception, we humans find it difficult to easily visualize the concept of an expanding universe. When we hear about the Big Bang, we often imagine an extremely compressed mass of matter exploding in a vast or infinite space. But this isn't accurate when it comes to the Big Bang. The truth is that all of space, including the matter and radiation within it, expanded from an infinitely small point. This theory is built upon foundations that exist in everyday life. For example, one can easily imagine a finite universe, like an inflating balloon, where all its inhabitants are flat beings living on its surface. The entire two-dimensional space of theirs can expand from the initial moment when the curvature is extremely large. When the small ball spins, the moment its curvature decreases is also when the balloon is inflated more. However, it is difficult for creatures to envision two multidimensional worlds expanding into some unified entity. Amber Einstein likened an astronaut to someone returning to their own point of departure. No matter how hard he tries to keep a straight line, when astronomers captured signals from the cosmic microwave background using a radio telescope, they are precisely measuring the temperature of the universe in its earliest stage. Decrease in proportion to how much the universe has expanded since its formation. When the universe was only 1/1000th of its current size, the temperature at that time was 1,000 times higher, around 3000 degrees Kelvin, not just 3 degrees as it is today. One of the most striking features of the current physical universe is the dominance of the Hero and Halley. Indirect evidence of the extremely high temperature state in the early universe, as predicted by the Big Bang theory. Halley's comet makes up about 28% of the mass of large particles in the universe, while the rest belongs to the Rho association. Only a small amount of heavy elements were formed from the explosion of massive stars. The relative difference between Halley and heat Rho can be most clearly explained. With temperatures reaching billions of Kelvin in the universe when it was just 3 minutes old. This temperature may have heated the helium released from the primordial nucleus shortly after the Big Bang occurred. In the first moments after the Big Bang, the temperature reaches over 100 billion Kelvin, and the material density is billions of times higher than that of iron under normal conditions on Earth. A swirling vortex of subatomic particles and radiation. The neutrinos, which were thought to be massless, stopped interacting with other particles, and become the independent foundation for the remaining matter in the universe. About 700,000 years after the Big Bang, radiation and matter remained in a state of equilibrium. But in the end, the cooling was just enough due to the expansion that occurred for negatively charged electrons to combine with light atomic nuclei, thereby forming complete atoms. The universe became transparent, facilitating the evolution of all celestial bodies. What we observe in the universe today, galaxies, stars, planets, and even cosmologists are striving to uncover all the mysteries of the universe. We all know that the modern universe is fundamentally governed by 4 basic forces. Gravity and electromagnetic forces govern the motion of electrons, causing them to orbit around the atomic nucleus. The weak force governs the radioactive decay of atomic nuclei, while the strong force binds particles within the nucleus. The quarks are bound together within the atomic nucleus. But let's rewind time to the very beginning, even before the first moment of the Big Bang explosion. There is compelling evidence proving that natural forces have merged into a single, all-encompassing form of force. If there is a lack of a theory capable of unifying all fundamental forces, we would understand very little about how the universe operates in nature when it was much smaller and hotter than it is now. Therefore, it is impossible to provide a satisfactory explanation for the origin of the universe. Although physicists cannot recreate the extremely high energy conditions of the early universe in the laboratory, but they need to develop theories to explain the reasons behind the existence of the natural forces that humans currently observe. Additionally, there are 4 distinct characteristics, and the way these forces are represented also differs. The world of subatomic particles includes components such as quarks, leptons, muons, tauons, and W and Z particles. Physicists are striving to construct the grand edifice of unified field theory, a lifelong pursuit of Einstein. Theories of this kind are called grand unified theories. The grand unified theory is the key to understanding the universe in its earliest moments, and they help predict what we expect to discover in the present-day universe. The 4 fundamental forces of the universe today do not always share many similarities with each other, but many mysteries still surround them, fueling endless speculation about their connection. The discovery of the W and Z particles proved that the electromagnetic force and the weak force are actually just 2 different manifestations of a single unified force. That is the weak nuclear force. Thanks to this, 2 fundamental forces of nature have been unified into one. Even if it's impossible to produce experimental evidence in the lab to prove consistency between the strong force and the gravitational force versus the weak electromagnetic force, the greatest experiment was the Big Bang. This could prove to be the ultimate test for the next great unified theories, where all fundamental forces converge. This is where cosmology and particle physics come together to solve shared mysteries. But it wasn't until 1979, when Alan Guth took the stage. Currently, no cosmological theory can explain how the Big Bang initiated within the first 1% of a second. After carefully considering the opinions of my colleagues, he came up with a strikingly fresh perspective on the workings of the Big Bang. This is the idea of cosmic inflation that he proposed. Unlike the initial hypothesis of a steady expansion rate accepted for the Big Bang, he proposed the hypothesis of an exponentially expanding universe, beginning around 10 to the power of -36 seconds after the Big Bang. The exponential expansion occurred at a breakneck pace, almost instantaneously, then ended in an astonishing manner. Created the energy source that gave birth to the universe. In an extremely tiny segment of the string, the universe expanded from a subatomic size by an enormous factor of 10 to the power of 50 times. But the diameter is still only about 4 inches. From that moment on, the expansion rate of the universe gradually stabilized and became more consistent over time. With a broad vision, Alan Guth analyzed the perplexing issues that have left cosmologists scratching their heads. His theory explained the reason why the universe exhibits significant large-scale homogeneity and isotropy. No matter the angle or the observer, it looks exactly the same. It can be predicted that from an initial chaotic mixture, regions of varying density will form. According to Alan Guth's theory, hyperinflation had the effect of leveling the differences between regions. Moreover, he provided a compelling explanation for the greatest mystery that modern cosmologists are currently trying to unravel. Why does the universe maintain a delicate balance between 2 states? Open, meaning endlessly expanding, and closed. Finally, it will inevitably collapse in an event similar to the Big Bang but in reverse. Since ancient times, cosmologists have always been acutely aware that they would face the problem of mass deficiency if the universe continued to expand infinitely, or even when it is in a balanced state between closed and open. All objects in the universe exert gravitational force on each other. This slows down the expansion of the universe, and if the mass is large enough, the universe could even collapse back on itself. But calculations show that the observed mass in the universe accounts for only 1% of the mass needed for it to collapse back on itself. Some scientists suggest that in the past, the amount of dark matter in galaxy clusters may have been sufficient to partially compensate for the missing mass. However, this additional mass likely meets only about 10% to 20% of the amount needed to trigger a collapse. About 80% to 90% of the remaining mass of the universe, necessary to maintain balance, may exist in another form. One hypothesis suggests that the missing matter could exist in the form of primordial black holes, formed very early when the universe was in an extremely dense state. One hypothesis suggests that the mysterious neutrinos permeating the universe may possess an extremely small mass. Although these particles have an extremely small mass, they could still be the answer to that deficit. And in fact, it could make up the majority of the universe's mass. According to Alan Goode's theory, an inevitable mathematical consequence is that the universe always maintains a perfect balance between an open state and a closed state. Cosmologist Mars Davis from the University of California said, "The explosion of Alan Gude will violently propel the universe to a critical state, precisely balanced between open and closed boundaries, with extreme accuracy." Therefore, Alan Guth's theory spurred cosmologists to redouble their efforts in searching for the missing mass, something they firmly believed must exist somewhere in the universe. It's understandable to sympathize with scientists when they face numerous challenges in tracking the complex equations that lead to this conclusion. However, it can be said that the physicists' nearly impenetrable equations, which describe how vacuum fields can exist, carry the very properties of matter. Here is the closest explanation science can offer about the origin of all things. Alan Gude likened the universe to a free lunch, formed from quantum fluctuations in an ancient vacuum. Broadly speaking, he hypothesized that gravitational energy precisely cancels out non-gravitational energy in the universe. The result is that the total energy in the universe is precisely zero. Your comrade would surely be dizzy trying to imagine how everything could literally emerge from nothingness. Only an ancient void has existed since the dawn of time, moving in accordance with nature's unified law. According to Alan Gude, inflation also implies that the actual universe is billions of times larger than the observable portion we can see. It itself spans billions of light years. If the universe's matter density exceeds the critical threshold, it will collapse on itself after billions of years, and all structures will vanish without a trace. Some people believe that afterward, it will bounce back and expand in a new Big Bang. The universe we currently live in may be just one of countless universes that have existed before, which could be similar to or different from our own. However, only the cosmological theory asserts that at least the observable part of the universe will continue to expand indefinitely. Even though gravity inevitably slows the expansion of space, it is still not strong enough to bring it to a complete halt. In other words, expansion is defined as a process that will continue indefinitely. This concept puzzles many people, as infinity is an elusive notion that poses significant challenges to the human mind when trying to comprehend it. Note that Guth's theory does not deny the existence of parallel universes, or permanent alternative realities beyond the scope of human observation. Other massive explosions may have occurred, giving rise to other universes, like separate space-time bubbles distinct from our own. Perhaps we cannot reach those universes, just as molecules on the surfaces of two inflating balloons cannot touch each other. What will become of all we see today? In our local forest, everyone knows that the sun will go through a red giant phase, expanding so much that it will engulf the Earth and melt the planet's surface. Only 5 billion years left. But even 5 billion more years will be just a fleeting moment compared to the infinite time ahead. Scientists have recently begun to hypothesize about the demise of the universe during its endless expansion. In the next 100 trillion years, every star in the universe will gradually exhaust its fuel. 100 million trillion years from now, every star in the universe will lose its planets due to random yet unavoidable collisions among them. The collapse of all galaxies will be complete after a quadrillion years, when all their stars have evaporated into intergalactic space. At times so distant they're beyond imagination, even stable particles like protons will eventually decay into unstable subatomic particles. Black holes will eventually evaporate after about 10 to the power of 100 years, and the universe by then will be nothing but an extremely thin gas with freely floating particles of matter. What meaning can we derive for our own lives from the picture of the universe's evolution? That picture becomes increasingly clearer as the boundaries of knowledge continue to expand. Some will look upon it with despairing eyes, as their faith in a benevolent creator is tested to the limit. One can find verifiable evidence for dubious intelligence within the very flow of this grand historical narrative. Certainly, many cosmologists may hold a pantheistic view of God, as the universe itself, in their conception, is the supreme being. God and the new physics believe in a universal mind that governs, permeates the cosmos, and directs the laws of nature to achieve certain purposes. This state of affairs can be expressed as follows. Nature is the product of its own technology. The universe is a mind, a self-observing and self-organizing system. No matter how different each person's perspective may be, it is truly astonishing how humans are captivated by calculations and spend countless hours gazing at the starry sky. Could encompass all of space, time, and even beyond. How meaningful it is that a part of the universe can contemplate itself. At the same time, I wonder if this life or any other could play a part in the cosmic drama about to unfold.